Hi everybody, today we're going to take a look at the 8-0 notes on simplifying radicals. So this should be a review from your Algebra 1 days, but we're going to run through a few just to kind of remind you. Everybody shows this a little different. I tend to use upside down division. Some people will use a factor tree, so I'll try and do a mix of them as we go through these problems. So in number 1, 63 is a number inside. All right, so when I'm teaching this in an Algebra 1 class, I'll usually tell people to look at 63 and then start running through the primes. So 2 goes into that, it doesn't. 3 does go into that, goes in 21 times. All right, 3 goes into 21 as well, but 7 times. 7's prime, so I now have my prime factorization. I look for pairs. I've got a pair of 3's, all right, which really means that I have a 9 underneath the radical sign. All right, and a 9 under the radical sign, we all know square root of 9 is 3, so I can bring 1 3 out front. And then I have that 7 that's left over, right, and it's stuck inside because I don't have a perfect square there. All right, again, the 3 could come out front because it was really a root 9 underneath. All right, so there's the first one. 3 root 7 would be an exact answer. So if I ever ask for exact answers, I'm looking for something like that. I'm not looking for a decimal. If I go over to 525, this one I'll do with a factor tree. So we have 525. 2 does not go into it. 3 does go into it, if we notice that. And again, you can check by the sum of the digits. If the sum of the digits, 5, 2, and 5, add up to 12, that's divisible by 3, so the whole thing is. So if we go through here, 525 divided by 3 gives me 175. All right, now 175, when I add those digits, I get 13. So I know that's not divisible by 3, but it ends in a 5, so I can say it's divisible by 5. All right, which gives me a 35. And 35 for my multiplication tables, I'd remember is 5 and 7. All right, so again, I'm looking for pairs. I've got a pair of 5s, because that's really going to give me a 25 if I broke this apart. Square root of 25 is 5, so I can bring a 5 out front. And then I look for the things that are left over. I've got a 3 left over by itself and a 7 by itself. So I have a 3 times 7 inside, which is 21. So I have 5 root 21. All right, and again, that would be the exact answer. If I wanted a decimal, I would say give me an approximation, and I'd tell you to what place value we'd like that. All right, if I take a look at the next one, now we're starting to do operations with radicals. So again, this is a squared. So first thing I'm going to do is I'm actually going to write this out as 3 root 3 times 3 root 3. Next thing I'm going to do is I'm going to use a commutative property, and I'm going to kind of regroup it so similar things are close together. So I'm going to leave the 3 times 3, and then the root 3 times root 3. All right, the 3 times 3 is a 9, and then root 3 times root 3 is going to be root 9. All right, but root 9 is 3, so we have 9 times 3, which is 27. All right, and I know this seems like a weird kind of silly problem. We're actually going to see this structure come up a ton when we do our Pythagorean theorem problems, because anytime one of the sides has a radical in it, then when we square that, we have to remember to square both the number in front as well as the radical. If I take a look at number 4, kind of looking at this from a little bit more advanced technique, one way to look at it is we can look at 3 squared and then root 2 squared, thinking about kind of distributing the exponent into each of the two pieces of the product. 3 squared is 9, and then root 2 squared would be root 4, which is just 2. 9 times 2 is an 18. All right, and again, I would probably say out of the beginning problems here, these two are the ones that are going to come up the most when we're working with our problems in this chapter. Going on to the next one, more operations. So here I notice, I can rearrange it like we did before. 2 times 3 times root 5 times root 15. 2 times 3 is 6. And then 5 times 15 is going to be 75. But now I have to go off to the side and I have to check the 75. All right, 75, 3 goes in there 25 times. 5 goes in there 5 times. I've got a pair of 5s. So I can bring a 5 out because that's really a root 25. So I have 6 times 5, and then I have square root. I still have the 3 that's left over, so it's inside. So we have 30 root 3. All right, looking at the next one, this one has a variable in it. Don't let that throw you off. Just kind of think of it the same way. So I've got 96 x squared. So if I was going to do a prime factorization, I might think 96 and x squared. Breaking the x up, I might think x and x. All right, the 96, both are divisible by 3. All right, so I can say 3 and 32. 32 breaks up, not divisible by 3, but it is divisible by 2, so I've got 2 and 16. 16 is 2 and 8. 8 is 2 and 4. 4 is 2 and 2. So I look for pairs. All right, pair of 2s, pair of 2s, extra 2, and then I got a pair of x's. All right, so I can bring a 2 out from the first pair, so that piece is dealt with. I can bring a 2 out from the next pair, that piece is dealt with. I can bring an x out from the pair of x's, that piece is dealt with. And then I have this lone 3 and 2 that are still hanging out there. So 3 times 2 is a 6, and that's going to be stuck inside. All right, now I clean it up a little bit. 2 times 2 is 4, so I have 4x on the outside, root 6 on the inside. All right, so that gets us through some of the kind of key techniques of this section. I'll be back in the second part of the video to look at rationalizing the denominator and one or two other weird things that we'll run into in this chapter. All right, hope that helped. Have a great day. Bye.